So we're talking about exponential functions, okay? Something that grows exponentially means it increases very fast. So we're talking about exponential functions. So here in part A, it shows you some old equations that you've worked with before. We've seen these quadratics and these cubics. The new stuff, take a look at the way it looks when it's new. You have exponents, you have the x variable, but the x is now your exponent. That's the new thing here, is putting your variable x in the exponent. This is the big change when the variable is in the exponent. Okay, big change. So be careful if you have any dyslexia that you don't confuse y equaling x squared with y equaling 2 to the x. Very different functions. So let's take a look at what in the world y equaling 2 to the x looks like. So I have a table here. We're going to put some values in this table, and we're going to be pretty extensive on this first example to make sure we can get this graph pretty clear. Okay, so suppose we have y equaling 2 to the x. Well, if I put a 0 in here, 2 to the power of 0, remember anything to the power of 0 equals 1, except 0 to the power of 0 is undefined. If I put a negative 1 in here, 2 to the power of negative 1, remember negative exponents, this is 1/2. If I put a negative 2 in here, this would be 2 to the power of negative 2, which is 1 over 2 squared, which is 1/4. If I put a negative 3, this would be 2 to the negative 3, which is 1 over 2 cubed, which is 1/8. Okay, so there's your negative exponents kind of coming into play. Now let's go with positive numbers. If I choose x to be 1, 2 to the first power, which is 2. If I choose x to be 2, 2 to the power of 2 is 4. And if I choose x to be 3, 2 cubed is 8. These numbers will get very big very fast. If x is 4, 2 to the fourth power is 6. So these grow very quickly. But we're really looking more around the origin, around the x value of 0 to kind of get this graph. So let's just graph it and see what it looks like. At negative 3, I'm just barely up above the x-axis at 1/8. I mean, this is not really 1/8. I'm just kind of putting something on the table to get it small and still visible. At negative 2, it's 1/4. Again, these are so close together that obviously these are not exactly on track. A little better at negative 1, 1/2. 0, 1. Actually, I'm not as low as I should be. Let me drop this one a little bit more. Okay. Like I said, these are all so close to the x-axis, it's hard to get them very accurate, but we're just kind of looking for a pattern anyway. Okay, 0, 1, then 1, 2, then 2, 4, then 3, 8, and 4, 16. It jumps all the way off the chart here. Okay, so you can see how quickly it's climbing. Okay, so it's very low, close to the x-axis, then it shoots and it climbs very quickly. In other words, it's climbing or growing exponentially. It's growing very quickly. That's why they call these exponential graphs, because it grows so quickly. And every exponential function, 2 to the x, 3 to the x, 4 to the x, 5 to the x, will all have this pattern where it's growing exponentially or growing vertically very quickly. Now, there will be a horizontal asymptote right here. Okay, your exponential functions will have a horizontal asymptote at y equaling 0. Okay, at y equaling 0. So in general, once you see that this is what a graph of an exponential function looks like, whether it's 2 to the x or 3 to the x or 4 to the x or 5 to the x or 6 to the x, they all have this same appearance. And they all have this same appearance. Okay, it is asking me what is the domain and what is the range. And the domain is all real numbers, negative infinity to infinity. But your range is limited. So you're starting at a y value kind of 0 and going up. Well, you don't ever actually touch the x-axis, so you don't get to have the 0, but your y values are going up to infinity very quickly. So there's your domain and your range of this exponential function y equaling 2 to the x. Now, let's go down and see if there's another one down here. Here's 3 to the x. and you're going to see a very similar pattern in 3 to the x. And so be sure you get 0 in here, -1, and 1. Those are the main 3 ordered pair of points that we are going to consistently need to use. The 0, the -1, and the 1. And then anything else around it is just extra. So if I put 0 in here, 3 to the power of 0 equals 1. 3 to the power of -1, remember, is 1/3. And I could keep going with the negatives. 3 to the power of -2 would be 1/9. And 3 to the power of -3 would be 1/27. And then let's play around with the positives. So 3 to the power of 1, that's easy. 3 squared is 9. 3 cubed is 27. So this moves up very, very quickly. These numbers get large very quickly. Okay, get very large very quickly. And so let's graph this one on the same graph to the best of our ability. So this graph is y equaling 2 to the x. And I guess I should change color here. I guess I'll change to blue, to y equaling 3 to the x. Well, my table I can't fit on here on this screen. But 3 to the power of 0 was once again 1. 3 to the power of -1 was 1/3, way down here. 3 to the power of -2 was 1/9, and then it was 1 to the 27th. It was so small that I really can't even get it on the graph. 3 to the first power was 3. 3 squared was 9. 3 cubed was 27. It is off the chart. So this graph was below the 2 to the x on the left. It was the same at the x value of 0, and then it climbed even faster than the 2 to the x on the right. So your blue line here would be your y equaling 3 to the x. So it's above it on the right side of 0 and below it to the left side of 0, but it has that same pattern of increasing very quickly. It has that same horizontal asymptote, same domain and range. Okay, all right, so one more. All of a sudden, what is this one? Oh, crud, e to the x. Well, this one, the values are so strange, okay, a little bit off here, that let's just kind of go with the typical -1, 0, 1, and let's call it pretty good. So anything to the power of 0 equals 1. So note that every one of these tables has this point 0, 1 in it. Every one of them share that y-intercept. If it's -1, well, e to the -1 is 1 over e, which is approximately 1 over 2.7. So we'll just put 1 over 2.7, pretty much 1/3. And then e to the first power is 2.7. Okay, now that's an approximation because that's an irrational number, e is. But now let's take a look at it on the graph. Okay, so 2.7. What we're going to see on the graph, and I guess I'll do this one in, I don't know what color is going to come out on the graph. Maybe I'll try this green. Okay, so it's also going through this same point 0, 1. So I'm really emphasizing the same y-intercept. And then at 1, it would be a little more than 1/3. It'd be right here in the middle. And at -1, I can't even get it in here, but it's in the middle. So your e to the x is going to be between your 2 to the x and your 3 to the x. It's going to be in here. It's going to be trapped between those two lines. Okay, it's trapped between the two lines, which makes sense because the value of e, 2.7, is between a 2 and a 3. So your base of 2 and your base of 3, the 2.7 is going to fall right between them. It's going to be trapped between them. So again, I want to really emphasize with these graphs, they all are increasing, which the book hasn't been emphasizing that. They are always increasing. They're always going up. They're increasing exponentially. They're increasing very quickly. They're always increasing. They all have the same domain and range, and they all go through that point 0, 1. and they all have the same horizontal asymptote y equaling 0. So if they want you to do y equal 5 to the x or y equal 4 to the x, it looks a whole lot like that. Always increasing, same domain, same range, same horizontal asymptote. Now, in general, every time we graph one of these exponential functions, we're going to be working mostly with x values of -1, 0, and 1. So once you have in your mind that you know it's always increasing, that it has that horizontal asymptote, you can pretty much just use those three values and be able to get a sketch of your graph. Okay, so those are the main three that we're going to continue to focus on. So then what they do is they start working with transformations on these graphs, like this next set. All of a sudden we're going to start shifting them left and right or up and down, flipping them over the x-axis kind of thing. So let's take a look at, they want me to graph y equaling 4 to the x plus 1. Well, to do the transformations, I'm just going to start with y equaling 4 to the x. It's going to be the always increasing, horizontal asymptote y equaling 0, and I'm going to try the three x values of 0, -1, and 1. Okay, that will give me just enough to be able to draw that always increasing, exponentially growing function. So at -1, what would this be? What is 4 to the -1? 1/4. 4 to the 0 is 1. We're always going to have that same y-intercept, and 4 to the first power is just 4. So this would be at -1, 1/4, which is so small on this graph it's hard to see, 0, 1, and then 1, 4. So this is your y equaling 4 to the x graph. Good enough. Okay, that's plenty good for us. Okay, that's good enough. We're not going to be right on with it, but that's plenty close. Now, if we say x plus 1, anything dealing with x is horizontal change. And if it's plus 1, that means which way? Left or the right one? Left 1. Left 1. If you're going left, you're only going to change your x value, right? If you're sliding to the left, your y value does not change. So your y values remain 1/4, 1, and 4. But if you're going left, you're going to subtract 1 from every x value. So -1 minus 1 is -2. 0 minus 1 is -1, and 1 minus 1 is 0. These will give you the 3 points shifting this exponential function to the left 1 unit. So I guess I better change color. I'll go with blue. This point to the left one would be about right here. This point to the left one would be here. And this point to the left one would be here, which would be the ones we have in our table. -2, 1/4, -1, 1, and 0, 4. And so this would be our transformed exponential function, y equaling 4 to the x plus 1. So we just took it left 1. Now, my transformed function has a horizontal asymptote. When I moved left, did it change the horizontal asymptote? No. So with horizontal asymptote remains y equaling 0 right here. Okay, so there it is, moved to the left 1. So you're going to see me really playing with the tables. So left 1, I'm going to write here, left 1 means x value minus 1. I don't know how to say that. From here to here, I'm going to subtract 1. That's what I'm doing. If I'm going left 1, I'm going to subtract 1 from every x value, and I'm not touching the y. Okay, so we only change the x values, not the y, if we're moving only left or right. Okay, so let's try another one. Okay, here's another transformation, 2 to the x plus 1. Right here, we know that this is going to be left 1, and then minus 3 will be down 3. Okay, so this is kind of the movement, the transformations of the parent function or the original function y equal 2 to the x. Okay, so the same three values. Well, I'm going to just do that wrong. Okay, -1, 0, and 1. You're going to hold to those values, and you're going to stick in your mind what that graph looks like, exponentially growing. Okay, to the -1 we know is 1/2. 2 to the 0 is 1, and 2 to the first power is 2. Okay, so now 2 to the x plus 1 is left 1. So if I go left 1, I take the x values, and what do? Subtract 1 from the x values. Your y value doesn't change if you're going to the left or the right, so leave the y value alone. But left 1 is subtracting 1 from every x value. Okay, so negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. And 1 minus 1 is 0. Okay, all right, now when we have the minus 3, this means down 3. When you're going down, you don't change x values, you only change y values. So now leave your x values the same, but when you go down 3, take your y value and subtract 3. Okay, subtract 3 from your y value. Okay, 1/2 minus 3 is what? 2.5, right? 1/2 minus 3 actually is a negative 2.5. 1 minus 3 is a negative 2. And 2 minus 3 is a negative 1. All right, let's try to graph it. Negative 2, negative 2.5, about right here. Negative 1, negative 2. 0, negative 1. Now you've got to remember this is an always increasing graph. Okay, where is my horizontal asymptote? If I dropped it 3 units, that horizontal asymptote would be y equaling what? If I go down 3 units, what will be my horizontal asymptote? Y equaling what? Negative 3. There you go. So it would be about right here. It's kind of hard to get this graph looking right without putting that asymptote in there. There's your horizontal asymptote. So here it is. You're hugging the asymptote, never crossing it, and then you start to climb pretty quickly. There is your transformed graph, y equaling 2 to the x plus 1 minus 3. Okay, so let's think about this. We started, okay, if you think about the steps, we started with something looking like this, y equaling 2 to the x. Whoops, except we went through 0, 1. Okay, so we looked like this going through the point 0, 1. We started like this. Then we moved it left 1. So when we shifted it left 1, this point moved here. So then it kind of looked like this, and it's climbing to the left. Then we took that line and moved it down 3 units, which ultimately gave me the black line which we just drew. Okay, so this asymptote, this blue asymptote, went down 3 units to here, which gives me my new horizontal asymptote at y equaling negative 3. Right there. Okay, now the goal is to start with your parent function and go immediately with the table, skipping the middle table is kind of the goal. We would like to eventually be able to skip that middle table. Okay, so what are the transformations? They're not going to actually ask me to graph it. What are the transformations with this given graph? Okay, so my parent function would be 3 to the x. Now, if I take it and put a negative in front of it, what does that do? The negative in the front, what does that do? Reflects it over what? Y'all sure are a quiet group this Monday morning. That negative in the front reflects it over the x-axis. And what does that plus 5 do? Up 5, right? Out on the end, the number on the far end is going to tell you how far up. So I'm not going to officially graph this, but I'm thinking you're starting like this. Step 1, there's my exponential function. When I reflect it with the horizontal asymptote right here, when I reflect it, it's going to look something like this. And then when I take that up 5 units, okay, so this was the point 0, 1, this is the point 0, -1. 1, 2, 3, 4, 5, it would be here. My final would look here. Okay, this would be my final kind of shifted graph image in my mind. So now my horizontal asymptote is here, and my new horizontal asymptote would be y equaling 5. So when it says what is the equation of the horizontal asymptote, it's y equaling 5. Okay, it's y equaling 5. Now, what is my domain of this thing? I have no restrictions on x. -infinity to infinity. But my range is something a little new now. What's my lowest y value? How low does it go? -infinity. But how high does it go? 5. There you go. Okay, so you can do a quick sketch like I just did. I'm very fortunate with this electronic version that I can tap off those lines as I was moving them around. But that's ultimately what the ending graph would look like. Okay, so here's another transformation. Now this one's not one that we're quite as familiar with. This one's a little bit different, so it's a good example in case you see it in your homework. Your original function, again, is 3 to the x. Now, when they put the negative on the x, if you replace an x with a negative x, then you're coming over the y-axis. So this is a reflection over the y-axis. So if you take x and replace it with negative x, if you can visualize that, you're coming over the y-axis. Then, after you've reflected it, you come in here and you subtract 9. That's going to take the graph down 9 units. Okay, this will be coming down 9 units. So 3 to the negative x minus 9 is now down 9 units. So if you try to visualize this one, your original graph is always increasing like this. When you reflect it over the x-axis, and it's going through 0, 1, when you reflect it over, the y-axis, it's going to look like this. Okay, there's your reflection. You still have that same horizontal asymptote. Now when you come down 9 units, 1, 2, 3, 4, 5, 6, 7, 8, 9, down here, your graph will look something like this. Okay, so 0, 1, down units, this will be 0, -8. So at -9 will be your horizontal asymptote. So now your horizontal asymptote will be at y equaling -9, and this looks a lot better on a piece of graph paper. Your domain remains the same, no restrictions from the left and right, but your range is really different this time. Okay, you're at a low value, not -9, but getting close to it, and you're going up as high as it wants to go. So that point 0, 1, sliding it around or transforming the point 0, 1 is kind of your guide to keep you in the right location on the graph. All right. Okay, so here's some more tables. Oh boy, here comes E. Don't ever be hesitant with E. Just remember it falls between 2 to the x and 3 to the x, and it looks like all the rest of them. Okay, so e to the x, 0, -1, 1. So this would be 1 over e, which is kind of like 1/3. E to the 0 is 1, and e to the first is just e. So it's 2.7s, very close to 3s. Okay, x plus 1, remember horizontal movement is the opposite of what you think it should be. This will be left 1 unit, which means your x values, if you're going left 1, your x values, you will subtract 1 from your x values. Your y values will be the same. You're not altering the y value, but the x values you're subtracting 1. So -1 minus 1 is -2. 0 minus 1 is negative 1, and 1 minus 1 is 0. So that would be shifting it left 1. Then the minus 2 means down 2. It's when you go up and down that you shift the horizontal asymptote with you. Okay, so going down 2, at this point you don't change your x's, but your y value, if you're going down 2, your y value will mean subtract 2 from your y's now. Oh boy, okay. So this is, I don't even know what this is, 1 over e minus 2. So about a third minus 2. So say it's a third minus 2, which would be what? A negative 1 2/3? Something like that? Okay, so then 1 minus 2 is easy, that's just a negative 1. And then e minus 2, again, is like 1/3 minus 2, which would be again like a negative, no, 1/3 minus 2. Hold on, I got something off here. The top one I got. Okay, no it's not. This is 2.7 minus 2, so this is about 0.7, so this is approximately 1/3. Okay, see if we can get this to work. Okay, negative 2, negative 1 and a third, kind of, that's somewhere like here, whatever. Negative 1, negative 1. So it's supposed to be above it, so I need to come down just a little bit more. Bless you. Here and here, and then 0 and about a third, something like this. So here it is. Okay, there it is. So when you went down 2, that would make this horizontal asymptote come down 2 from its original position on the x-axis, making your horizontal asymptote y equaling negative 2. So with e, we do a little more kind of estimating, and you can put e on the calculator if you really want to see the decimal values. All right. So what's the next one? Here's another one. This one we just want to talk about it. Okay, we're not going to graph it, we're just going to talk about it. So your parent function is y equaling e to the x. Then they come in here and they put an x minus 3. So when you're fooling around with x, it's horizontal change. And so this would be right 3. Then when you put the negative in front of it, that's reflecting over, this is the reflection we do real frequently, the x-axis. And then when you take all of that and you add 7, what is that? Up or down? Up 7.
Did you change x minus 3 to x plus 3?
Oh, I sure did. Okay. Up 7. It's the up-down that changes your horizontal asymptote. So if you were originally at y equaling 0 for your horizontal asymptote, if you go up 7, your horizontal asymptote will be y equaling 7. Okay, so these take a little practice, but don't be intimidated by e. I know it looks bad, it's a little uncomfortable. Just remember it's just that weird number about 2.7. Okay, now we come with a whole new game. Now part C is graphing exponential functions. They're still exponential functions. Your exponent is still x, but now your base is a fraction. Instead of it being 2 or 3 or 4 or 5 or e, your base is like a half or a third or a fifth. That makes a very different outcome. Okay, a really different outcome. So then we're going to stick with a few values here. 1/2 to the x. Okay, so I'm definitely going to put 0 in here, -1 in here, and 1. And I'm having a hard time fitting this all on my graph. But this first one is 1/2 to the x, and then we're going to compare them side by side as they vary the fraction just a little bit. Okay, Careful, careful. 1/2 to the power of 0, anything to the power of 0 is 1. What is 1/2 to the power of -1? It's 2. With that, what is 1/2 to the power of -2? 4. Okay, then 1/2 to the power of 1 is 1/2. 1/2 to the power of 2 is 1/4. Okay, so this is 1/2 to the power of x. What in the world does that look like? Let's take a look at it. -2, 4. -1, 2. 0, 1. There's that same y-intercept. 1, 1/2. 2, 1/4. 3, 1/8. And this is what it looks like. There it is. Looks very different. Okay, so this is my sketch of y equaling 1/2 to the power of x. Okay, so the next one is 1/3 to the power of x. I guess I'll do it in blue. Let me confirm. It's 1/3 to the power of x. So I'm going to put it here so I can have it better, more of my table showing. So I'm going to go 0, -1, -2, 1, and 2. Just enough to get a vision of the graph. Okay, so 1/3 of the power of 0 is 1. That's the easy one. Always, just 0, 1. 1/3 of the -1 is 3. 1/3 of the -2 is 9. 1/3 of the first power is 1/3. 1/3 to the second power is 1/9. And if you want to put another one on here because I have room, 1/3 to the power of 3 would be 1/27. You can see these numbers get very small and very large quickly, changing very quickly. Okay, so in blue, -2, 9, -1, 3, 0, 1, that same y-intercept, 1, 1/3, which is less than a half, 2, 1/9, which is less than a fourth. So we're above on the left and below it on the right. That's a pretty rough graph I just drew. It's not that easy to do with these pens. Okay, something like that. All right, so the blue one is my y equaling 1/3 to the x. And on E, this last one, which is f of x equaling 1/e to the x, remember E is approximately 2.72, so 2.7 is good. Right? So this famous 0, 1, they're all going through 0, 1. So this is e to the x. So e to the first power is e. Hold on, that's not right. It's 1/e to the x. We've already done e to the x. I think I'll change it. What did I use before? Green. Okay. So 1/e to the x. Okay. So 1/e to the first power is 1/e, which is real close to a third. It's 1/2.7. If it's -1, it's actually going to be e, which is about 2.7. And that's all we're going to do. Okay, we're not going to get any more detailed than that. But what you're going to discover, just as with e to the x, this 1/e to the x will fall between 1/2 to the x and 1/3 to the x. It will be right between the lines, and that will be your y equaling 1/e to the x. So with every one of these, we're going to have the same domain, the same range, and still the same horizontal asymptote. We still have the same horizontal asymptote, which is the x-axis, whose equation is y equaling 0. So every one of these will have a domain of -infinity to infinity, Every one of them will have a domain of negative infinity to infinity. And a range where they're all positive, 0 and up. They never actually get to the x-axis, so it's an open parentheses 0 to infinity, 0 to infinity, and 0 to infinity. And they all have the exact same horizontal asymptote at y equaling 0. Okay, and every one of them, these are always decreasing. Instead of increasing, when you have the fraction, you're going to always be going down, always decreasing when you have the fraction to the variable of x. Now when you look at these notes online in D2L when I post them, you'll be able to see the color. But of course, if you have a black and white printer, it's going to print in black and white. So be very careful about printing these. If you print them in color, you'll be able to see all these graphs in the blue and the green and the black. I hope they print okay. All right, so here's a transformation. Isn't this lovely? This is where it gets a little confusing, gets a little bit harder here. Okay, but as you can see on this first one, you're just going to start. All of these, well, the horizontal asymptote is going to change, and so will the domain and range, so we better stop there. Okay, so y equaling 1/2 to the x. Those same three x values, 0, -1, and 1 will be good enough. We know it's always decreasing. 1/2 to the 0 is 1. We're always going to go through that same y-intercept of 0, 1 on every one of these we have until we start sliding it. At -1, this is 2, and 1/2 to the first power is 1/2. That's my original, always decreasing exponential function when the base is a fraction less than 1. Okay, so now if I take x minus 3, this is to the right 3 units. Okay, x minus 3 is a horizontal change, and it's actually right 3 units. So x value only changes. The y values remain the same. Okay, so -1 plus 3 is 2, 0 plus 3 is 3, and 1 plus 3 is 4. Now, if I add 4 on the end, this is up 4 units. Here's where the horizontal asymptote is going to change. It was at y equaling 0. It's now going to be y equaling 4. If I go up 4 units, that horizontal asymptote is going up 4 units also. Okay, so now the y value changes in that I add 4. Okay, 2 plus 4 is 6, 1 plus 4 is 5, and 1/2 plus 4 is 4 1/2. Now you've got to keep in your mind this image, this was always decreasing. Okay, so 2, 6, 3, 5, always decreasing, and 4, 4 1/2. So it's coming down, it's decreasing, it looks like this. There it is, transformed. So your domain, even though it looks like it's going straight up, it is going left a little bit very slowly. But your range starts at 4, where the horizontal asymptote is, and then goes up to infinity. So the fractions are a little different. Okay, they look kind of weird. You just have to remember in your mind they're always decreasing, they're going down. The fractions are you're always going down. Okay, so now is when it gets pretty interesting. Here's where we get into some stuff, compound interest and exponential functions. Okay, so now we're looking at applications. We're going to kind of drop the algebra and get into some serious applications here. What in the world is compound interest? Compound interest is interest on interest, and sometimes that is hard for students to understand. So we're going to take a very basic example. If you invest $500 in the bank and you don't touch it, and they promise you 10% interest, which is very unreal, but it's just easy to make the computations, okay? They're promising you 10% interest at the end of every month. So in other words, you start with $500, then they tack on interest. Well, 10% of 500 is $50 in interest, right? At the end of the month. So now the new amount that you have in the account is $550. Okay? So then the amount in the account, you now have $550. So at the end of month 2, because you don't take it out, at the end of month 2, they have to add 10% to it, which in this case is $55. So now the amount in the account is $605. Okay, so now you're saying, I'm going to leave it in there. It's a pretty good deal. If I don't need to use it, I'm going to leave it in there. So now if I have $605, the interest is 10%. It's $60.50, right? So now I have, what, $665.50. So you started out with $50 interest. But now they added, because your amount in your account increased, you got interest on interest of $5 more. Then you got interest on interest of $5.50. And the next interest would be more. So that's called compound interest, where they're having to put interest on the interest they already gave you. Okay, they're having to add more interest because they're calculating it on the $50 they gave you. They got another $5 interest. So that's called compound interest because it is interest upon interest. So if you're investing money, this is a pretty good deal. Okay? But if you take out a loan, that's not a good deal. Okay? So it goes two ways. It depends on if you're investing money or if you're getting a loan. Because if you're taking out a loan, you are the one paying all the compound interest. All right, so let's look at something here. Here come all these formulas, and don't panic. Okay, you don't have to memorize this. I'm going to let you use this on a test. Simple interest is just what we did. Every month they compute that same thing that we did. Compound interest, now this is the serious equation. And continuously compounding interest, there's that E that I told you comes into play sometimes in financing, but a lot in your biologies and your sciences. So what do all these letters mean? Well, your A is the amount after the money's been in the account for a long time. Your P is your initial amount of money, okay? This is your initial amount. Would be like if you had that original $500, that's your P, your start value. Now, your T, okay, your T, which is up here in the exponent, really tiny, your T is the number of years. So instead of leaving it in there a few months, you might commit to leave it in there for 10 years. Okay, so your T is number of years. Your R is your interest rate. So, if they said your interest rate was 10%, you would use an R value of 0.10. So you lose the percent, you move that decimal over to get the number where you need it. The N is the number you've got to be smart about. If your N is the number of compounds per year, if you only compound it annually, that means they only calculate interest one time a year. So if you leave it in there 10 years, they calculate interest 10 times. But most people actually do it monthly. So interest is calculated at the end of every month. So N would be 12 if you were doing it monthly, once if you were doing it annually, 2 if it's semi-annually, and 4 times if it's 4 times a year, every 3 months. Okay? And this is the big equation. Okay, so now that we have the equation, this is the one we really use. We're going to move down. This continuous compounding interest means the computer is calculating it as quickly as it can. It doesn't just do it once a month, or once a day, or once an hour, or once a minute, or once a second. It's calculating it as quickly as it can generate it, continuously. So that would be this formula on the right, which we will apply on an example and give it a little more logic.
Wait, what was the 12 is
Monthly. Okay. All right. Monthly is 12. Okay. So let's take a look. Suppose $2,500 is invested in an account at 6% interest compounded for 10 years. Okay. So there's that number of years, 10. We got that. 6% interest, that's my R. So with that original sentence, then my P is 2,500. My R is 0.06. And my T will be 10. Okay, so those three values I have off that first real short statement. So part A says, what will be the amount in the account if you compound it quarterly? Quarterly means 4 times a year, so N would be 4. That looks like a 0.4, but it's not. That's a 4. Move my cursor, okay? It's a 4. So in part A, the amount in your account, if you don't touch it for 10 years, your formula is P times 1 plus R over N to the power of NT. That's the formula, and you don't have to memorize it. Okay, so my P is 2,500. 1 plus my R is 0.06. My N is 4. My N is 4 times T, which is 10. Okay, so this becomes 2,500 times 1 plus, and let's see if this is a nice value or not. Let me take 0.06 and divide it by 4, and that turns out to be a nice value. It just turns out to be 0.015, and this would be a 40, 4 times 10. So this is now 2,500 times 1.015 to the power of 40. Now when you put this in your calculator, you must first compute the 1.015 to the 40, and the last thing you do is multiply it times 2,500. So you take 1.015 to the power of 40, hit enter, then take and just put times. Don't repeat the number, just put times 2,500. Let that calculator hold as many decimals as possible, and you're going to come up with a value of 4,535.05. So $2,500 up to $4,500. So it didn't double, but it came pretty close to doubling. That's pretty good. You know, if you invested $50,000 and after 10 years you had $100,000, you wouldn't be too disappointed about that. Okay, so that would be the amount after 10 years invested at quarterly compounding interest. What is the total interest you earned? What did the bank have to give you since they took your money and held it tight for 10 years? Well, it would be your total of 4535.05 minus your original of 2,500, right? That would be how much the bank paid you for taking your money and not letting you touch it for 10 years. That's the interest that the bank pays you. Now you would think on part B, it says continuous compounding. This is where the E comes in. This is the formula where the E comes into play. So this is A equaling PE to the RT. This is kind of uncommon in the business world, but it's not as dramatic as you would think it would be in any form. So this would be your same principle of $2,500. E, which your calculator is going to use that. R, which is 0.06, and your T is still 10 years. So this is 2,500 e to the power of 0.06 times 10, which is going to be just 0.6. Now again, when you put this in the calculator, you have to do the e to the power of 0.6 first. And e is on your calculator above your division symbol. So if you take e to the power of 0.6 and let the calculator hold it, then just hit times 2,500, it will give you the result, which on my calculator is 4,555.30. So it's still a large amount, but it's only, what, about $15 more than doing it quarterly? So compounding continuously is not that dramatic a change. Even though it seems like it would be, it's not. Okay, so now let's get a little more serious about purchasing a home. You guys are going to get your degree. After you get your degree and you get a job, you're probably going to want to buy a home. So let's take a look about what life is like when you buy a home. Suppose you get a starter home for $150,000, and this is not a fancy home, okay? This is not a fancy home, but it's a nice enough home. It's $150,000. You qualify for an amazing interest rate of 4% because you're a first-time purchase, first-time buyer. Okay, back when I was your age, the interest rate was 12% for purchasing a home. It was terrible, okay? So it's 4%. Everybody, except for math teachers, finance their home for 30 years. Everybody. They just assume it. And unless you say something, they just say 30 years. Unless you say, no, I don't want to do that. It's automatic, 30 years. You ask your parents, how many years did you finance this home? They'll say 30 years, unless they're a math person. Okay. Okay. You make monthly payments. We all make monthly payments. How much do you pay for the home? Here we go. A equals P. This is the compound interest, not the continuous. So it's 1 plus R over N to the power of NT. Okay, so here we go. You're now taking a loan for $150,000 from the bank. This becomes 1 plus your R value is 0.04. Your time is 30. Okay, so this is going to be 0.04, and since it's monthly payments, your N equals 12. So this is over 12, and this is 12 times 30 years. So this becomes $150,000 times, and I'm going to see if this is a nice number, 0.04 divided by 12. It's not really good, okay? But this would end up being 1.00 and a bunch of threes. And believe me, the bank lets those threes go, okay? For 12, 15, 16 digits, all right? To the power of 360. So actually, I'm not going to, my calculator I think goes out to 12 digits, and I'm going to leave all 12 there. Okay, so it can be realistic. So remember, you take this value first. So I'm going to take this number in my calculator to the power of 360 and get a result, and I screwed it up. Okay, let me try it again. For somehow I messed it up. Okay, to the power of 360, there we go, times 150,000. The amount paid for the home is there it is. Almost $500,000 for your $150,000 home. That's exactly right. This is not playing around. This is some serious stuff, and this is exactly why math teachers don't ever finance a home for 30 years. Okay, your home would be $497,000, 24.70 cents. That's how much you would pay for your home. But that's pretty much everybody does, which is why the bank owns every home out there, unless you got a math teacher owning a home out there. Okay? So I wonder how much interest you actually pay for your home. How much is the bank making off of you because you financed it at an amazing interest rate, but you financed it for 30 years? So do you think the bank loves to finance homes? There it is. That's how much interest the bank will make off of that home. Off of every home. When you're when you're on a plane and you're lifting off over Houston, Texas, and you look down out of that window and every one of those rooftops, all that interest that's going to the bank. That's exactly the way it is. So the goal is you don't ever finance a home for 30 years. Okay, you get smart and you really finance it for more like 15, and you can. Okay, you just have to ask for it. your monthly payments will be a little higher. So your starter home needs to be more reasonable, or you need to save up some money for a nice deposit to make sure you can get that number of years financed off of 30. So when you hear people selling on TV or in the radio, refinance your home, hopefully they're refinancing it so they're bringing it down off of a 30-year note down to a 15-year note. People who were like me and had 12% interest, which I never did, I stayed in an apartment at that time, at 12% interest, they were quick to refinance when the rates came down because it was just horrible paying that kind of interest. Okay, so let's suppose you're buying a vehicle. This is something kind of common. Suppose you go out there and you buy a $35,000 vehicle. Maybe it's a nice truck. Okay, and that's a nice truck. That's not a fancy truck, okay, but that's a nice truck for $35,000, brand new. So suppose you go out there and you buy a $35,000 truck, and that salesman's going to rip you off because he's going to have you finance it for 7 years instead of 3 or 5 years. And as a first-time financer, you're probably only going to get about 8%. Okay, if you have good credit, you can get that down a lot lower than that. But first-time buyers, your interest rates are pretty high. So I'm going to say your rate is 8%. So 0.08, and your time is 7 years. So we do the same thing because in general you make monthly payments. So your N equals 12. And I'm glad I'm shocking all of you out there. Every time I teach college algebra, I think if this is the only thing I teach all those students in college algebra, it's a good thing. Okay, so here we go. 1 plus R over N to the NT. Okay, so you're going to go out there and you're going to get a loan for $35,000. And believe me, those car salesmen will never show you these numbers. Car salesmen do not like me when I walk in the door because I give them a really hard time. Okay, 12. N is 12, time is 7, and your interest rate is 0.08. Okay, so this is 35,000. I'm going to see if 0.08 divided by 12 is a nice number, and it should be. It's not a nice number. So this becomes 1.00, and then there's a bunch of sixes, and believe me, they'll put those sixes out as far as they can because that's that much more money in the pocket of the bank. Okay, this is going to be an 84. So remember, you must take this value and don't round it off. Leave it in your calculator of those 10, 12 digits on your calculator. So you're going to come in here, and really what you do is you take 0.08 and divide it by 12, hit enter, hold it in your calculator, add 1 to it. Hold on, that came out a little different. What did y'all get when you took 0.08 times divided by 12? Did y'all get 0.96? Okay, what did I do wrong here? Oh, okay, I did something wrong. Okay, so that's right. You're going to take that 0.00666666 on your calculator, add 1 to it. So now you have a 1.00666666. Take that to the power of 84, and then times 35,000. And then you'll find out what you pay for your truck. $61,159.77. Okay. That's pretty bad for you to pay $60,000 for your first vehicle. Okay. You really should not do that. Really should not. You really don't have to have an expensive vehicle when you're right out of college or right out of high school. You should limit that, and you should limit all these expenses so you can get on your feet before you get into so much debt. Okay, a lot of debt. So what is the interest you would pay? Well, you thought you were paying $35,000 for your truck, but you really paid $61,159.77. But that car salesman was quick to convince you to go for 7 years. They've got all those printouts just ready to throw out there at you just to try to tell you, oh, you can afford this monthly payment. We'll just finance it a little bit longer. 7-year financing didn't even exist when I was your age. 5 years was the maximum you could go. The interest you pay is $26,159. You could have bought 2 cars. Okay. Big stuff, really important stuff. Now, these exponential functions and applications of these, we do have a little time. Here's where we start finally getting into really where the continuous interest is important, where it's really applied. And it's applied in half-life when you start looking at more of your biology type applications. It talks here about the half-life of a radioactive substance. And so it talks about the half-life being equal to the amount of time it takes to decrease a substance to half of its original size. So how much time does it take for something to decompose to half of its original size? And so here comes an equation, and this one just has your exponential function in it. It talks about plutonium. It says a weapon-grade plutonium is composed by approximately 93% of this plutonium-239. The half-life is 24,000 years for that thing to decrease. In a sample originally containing 0.5 kilograms, here's your equation. Evaluate the function for the given values and interpret the meaning of it. So A of 24,000, your T would be 24,000. So this would be 0.5, a half, and this would be 24,000 over 24,000 because your T is the numerator in this application. So this becomes 0.5 times a half, right? 0.5 times a half, which is 0.25 or 1/4. Okay, so what would the amount be? Okay, if your time is 24,000 years, how did this work? The amount, okay, so this is how they came up with the equation. So it would be down to a fourth of its size after 24,000 years, which means it already decomposed half, and now it decomposes half again, which puts it down to a quarter of its original size. Okay, so that's what that means. And then you'd plug in the 72,000. We're running short on time. Here's another example where you can see an exponential function where you want to put a 4 in for your t. And again, we're running out of time. I was hoping we would get a half-life in here, but I don't see one to have a chance to review it. So we'll probably have to finish this up in our next class period because time is running short. But more importantly, the most important thing I really wanted to talk to you today about was financing a home and financing a vehicle. Be very aware of how that works, really aware. Try to put as much of a down payment down as you can and get your interest rate as low as you can, and the number of years you finance as minimal as possible.